All right, ladies and gentlemen, welcome back to the drive-thru. Hope everyone's having a wonderful week. As always, the drive-thru is sponsored by the deli. Looking to increase your vegetable intake? Stop by the deli. Get yourself some veggie straws, which counts. It counts. According to the school, it counts. We're on a veggie competition, and I'm dominating at eating trans fat-filled veggie straws. Don't look at me like I'm getting fatter. I know I am. No, the contest is to eat more vegetables. I'm going to win the contest and sell my Fitbit for a bunch of candy. All right, here we go. This is 12.5. It's chain rules. You already know a chain rule. Now we're going to know two chains rules. No? Okay. Here we go. Okay, so the first one is when we have one independent variable. So this means W is a function of F. Well, W is equal to a function that contains X's and Y's. However, X is a function of T and Y is a function of T. Okay, if you have all of those given pieces of information, then the change in W with respect to T, dW dt, is equal to dW dx times dx dt. So the change in W with respect to X times the change in X with respect to T plus dW dy dt. Okay? So this is taking our total differentials and kind of taking it, one level further. That probably doesn't do a whole lot for you guys, so let's do an example. Okay? If you're taking these notes down by any chance, then you can follow along in the book, because as always, they're out of the book. Okay, so here you understand what we're talking about. We've got a function W. Okay? It's a function of X and Y. So W is a function of X and Y. However, X itself is a function of T, but luckily Y is also just a function of T, so we can apply this chain rule. So the best thing you can do is just write down everything. dW dx. So that's the partial. That's the same thing as f's of X and Y. Okay, that's the same thing as the partial derivative of W with respect to X. So please let me know when I make a mistake. That's 2xy, and then the y squared is going to be gone because it's a constant, right? dW dy equals x squared minus 2y. Okay? dx dt is equal to cosine of t, and dy dt, e to the t. Okay, I haven't done e's in a little bit. All right, so then we know that dw dt is equal to, okay, dw dx, so 2xy times cosine of t dw dx times dx dt plus, okay, dw dy x squared plus y plus 2y, thank you, minus 2y times e to the t. Okay, but we're not done yet, okay, because we don't want x's and y's if we're talking about our change in W with respect to t. But luckily, x is a function of t and y is a function of t. So we will rewrite dw dt as Okay, 2x. 2 sine t y e to the t times cosine t plus x squared. Okay, that's sine squared t minus 2 e to the t times e to the t, and we'll just keep it like that. That is the change in w with respect to t. Now, hopefully you're thinking, well, why didn't we just substitute it in the first place? Okay, that's totally street legal. Just sometimes it's not going to be as fast. And you guys are going to learn when to use which ones. And I never care which ones you use. Okay, so if we just substitute it. Alright, so all you would do is take your original w function and substitute it in. So that's equal to sine squared t e to the t minus e to the 2t. Did I do that right? So, now I just act like I'm a junior in high school, and I was so, ignorant, and I'm just going to take this derivative like I didn't know what else was going on. So I just take this derivative with respect to t. This is going to get ugly, isn't it? So, first times the derivative of the second. So sine squared t times the derivative of the second, e to the t, plus second, e to the t, times the derivative of the first. Derivative of sine squared of t, 2 sine t cosine t. Is that right? All right. Yep. Remember that sine squared, let me just go to a new page. Sine squared of t actually is sine of t squared. So when we do our old school chain rule, the derivative of this with respect to t is 2 times what's left inside to the first times the derivative of what's inside. Right? Okay? Okay. We're not done with this one because we also have to take the derivative of e minus e to the 2t. That's negative 2 e to the 2t. And it is the same thing. It is the same thing. Okay? So you can do whichever one you want. Good? All right. Blink, blink. Okay, so now it gets more complicated. Now you've got w is a function of x and y, but x itself is a multivariable function. And so is y. Okay? So this one says, okay, first of all, there's just going to be two different ones. So this actually isn't any more work. It's just you have two options. You can find dw ds. Any guesses on what that's going to be? dy ds. So if you look, there's some canceling that goes on there that you can kind of, but that got Josh and I into trouble yesterday because we had deltas and we had Greek d's and but we're going to have to figure that out at some point before we get into differential equations. It's all right, we have time. And then you also can find dw, let's see, dt, and that's going to be dw dx dx dt plus dw dy dt, okay? So, if you're wondering where this is going, eventually we're going to start optimizing functions of multiple variables. And optimization problems are one of the key parts of calculus. So, all of this stuff that you're doing will eventually have an application, okay? You're also going to be able to isolate individual differentials for different variables within a problem. So, here we go. We got to find dw ds and dw dt. So here, what we're going to do is find dw dx, dw dy, dx ds, dx dy. Oh my gosh, we have z's too. Okay, so we have dy. Let's go in the same order. ds, dy. Hold on. dx ds, dx dt. Thank you. dy ds, dy dt, dz ds, and dz dt. Okay? And so the key is here, don't spend any time complaining about them because it's not going to save you any time from doing the problem. If you feel like pop them in your calculator, then go for it. Whatever success that, whatever feeling that gives you. Okay, all right, dw dx, what is it? Y plus z. It's y plus z, right? Let me change fonts so it stands out a little bit more. Okay, so now it's going to get fast. dw dy then is probably x plus z, isn't it? There's a lot of symmetry in these types of problems. dx is probably that. dx ds? No, that's too early. In fact, we left one out, didn't we? We left out dx dz because I forgot there was a z, so we'll write that here. dw dz is x plus y. Okay, here we go. Back to it. dx ds, cosine t. You guys agree? dx dt. S sine, no, negative S sine of t. Okay, dy ds sine of t. Dy dt is S cosine of t. dz ds is 0. dz dt is 1. The total differential will be, okay, so y plus z, dw dx times dx ds times cosine of t plus x plus z times dy dt. We are doing, I better write down what we're doing. dw dt, right? Is that what we're doing? ds. Yep, that's what I thought. Okay, so this was dw dy times dy ds. Where's dy ds? Sine of t plus x plus y times 0 Okay, and then I have to plug in s cosine of t and s sine of t, because we want it in terms of s's and t's. So it will be s sine of t plus z t times cosine of t plus x equals s cosine of t plus t times sine of t plus 0. That's it. And we're just going to have faith that we can find dw dt. So omit. Okay? No one was going to watch that. Come on. All right, almost done. Implicit differentiation. Okay, last part of the video. Yeah, I like that implicitly. It implicitly spells it right. It's just, exactly. Okay. So, if it's kind of important that you read the proof, because the proof is actually really easy to understand. Okay? If you've got a situation where you have f of x comma y equal to 0, then you want to use implicit differentiation. So, to find change in y with respect to x, it's a little counterintuitive, and this is why I encourage you to read the proof. It's actually the negative partial derivative with respect to x over the partial derivative with respect to y of that function. And we'll do an example. I think you understand it. Okay? If you've got more than two variables, then you've got two different partials, and I encourage you just to read the box in your book for that. But we predominantly will just be doing examples and situations that look something like this. Okay? So find dy dx. Well, notice since it's already equal to 0, then we have f of x comma y is indeed y cubed plus y squared minus 5y minus x squared plus 4. I don't know. Do you guys remember how you would do this? Well, every time you took the derivative with respect to what? With respect to y, you would write dy dx time of it. And then you would group all your dy dx's together, and then you would make parentheses, and you'd divide everything by that, and then, well, bam, you'd have your dy dx. Well, this is just easier. So this is an easier way to do something that you already knew how to do. Okay? Look, what's f sub x? It's a negative 2x, so the opposite of f sub x is positive 2x, right? Because we're going to end up wanting this. F sub y? Okay, so dy dx is 2x over 3y squared plus 2y minus 5. That's how it would work. So, can I get a small but aggressive boo?